Welcome to episode 14 of Roid Rage. We have our second external guest on, who's been working with us pretty closely for the past couple months, and we're really excited to have her on. So I'm going to welcome Dr. Cristina Thomas. I'm going to let her tell you a little bit about herself, and then we're going to talk about everything asteroids today. So with that, Cristina, would love to know who you are and what you do on your day job aside from putting up with us.
All right. So my day job is I'm an associate professor at Northern Arizona University in the Department of Astronomy and Planetary Science. And so that's kind of a mouthful. But I spend most of my time thinking about spectroscopy of asteroids and to think about what the populations look like, what can we learn about individual objects, and I've spent a lot of time thinking about this specifically with respect to the near Earth object population. Um, One of the biggest things that I've been involved with, especially in terms of planetary defense, which is a big part of the field, is I was the observations working group lead for the DART mission. So, NASA a few years back, crashed their spacecraft into the moon of a binary asteroid and changed that orbital period. And so I was in charge of the ground-based campaign to study the orbit before and after so that we understood the period change. And so that has been many years of my life, but really the thing that I keep coming back to is spectroscopy and really thinking about the compositions and the meteorite analogs and how all these pieces fit together, especially in the near Earth population.
Awesome. Uh, Help us understand, at what point in your life do you say spectroscopy is a thing that I want to study about asteroids?
Yeah, I mean that's kind of a strange choice. I will give you that. And so I've been interested in planetary science for a very long time. And when I was an undergraduate at Caltech, one of the professors brought a book to one of the classes, and I didn't actually realize that you could connect meteorites and asteroids using spectroscopy. And it was, of course, the easiest of the assignments possible. It was Vesta and the HED meteorites, which is they're dead ringers for each other. Everyone,
Yep.
pat themselves on the back, and it was great. And I thought, wow, I should totally do this. And it turned out it was way more complex than that when we moved on to basically everything else. But I've been doing that essentially ever since.
Got it. So you
Hold
got
on,
suckered
slow
in.
down for me. I'm kind of dumb.
That
Um,
was yeah, that was a
why
lot
is
really fast.
you said Vesta's the easiest one to get spectrum off of? Can you help me understand? Like, what are we? I hear this word all the time. Like, we're getting spectral images. Like, I can
Mhm.
assume I know what that means. I actually have no real idea what that means and what frequencies you're going over. But also,
Sure.
like, why is Vesta easy and why are others hard?
Well, Vesta is easy, partially because it's really, really large and it's really bright. As
How
a,
big is it?
I don't know. That's not my thing. But someone knows. And so it's really large. It's in the
I
intermain
bet
belt.
Al knows.
Yeah, and it's that means that we can get really high quality data off of it. And so, back with some of the initial spectrographs, that was in visible wavelengths. And so something like zero point 0.4 to zero point 0.9 microns. And now we tend to use near infrared as well, going out to about 2.5 microns pretty easily. And so the thing that makes this connection really easy to the meteorites is that it has a really distinct spectrum. It has these really, large absorption features at 1 and 2 microns. They're big. They look very unique. And we can do this match to the same wavelength region of meteorite spectra. And so we can basically say, look, they all belong together. And there's some nuance in there. There's three different kinds of meteorites that we think came from Vesta. And so that's HED, howardite, eucrite, and diogenite, which we think are different parts of the crust
Okay, hold
down
on,
into the
Christina. I
mantle.
got so many questions, and I'm just actually have no idea what you're talking about.
Sure.
At when you say like these things are absorbed at 1 and 2 nanometers, so I'm assuming like I'm looking at the spectral line, and you have it over, and like you have this peak at 1 nanometer and peak at 2 nanometers.
Dip.
Dip. Okay,
Do
so
a
it goes
big
the
dip.
other
Yep.
way, down
Yep.
instead of up. What does that actually tell me? Like, okay, so that's absorbed by the asteroid and doesn't get returned back to us. At 1 nanometer, what does that mean? Does that mean it's dirt? Does that mean it's a piece of iron? Does that mean it's I,
That in this specific case, you're looking at the specific minerals, and so the minerals have a really specific structure, and the structure that we're looking at is actually able to absorb the light because it does all sorts of very complex physical interactions, right? We don't need to talk about like physical chemistry right
Please
now.
don't. I'm already
Yeah.
confused on that. It absorbs instead of rejects. So like, don't go any lower for me.
So a lot of this stuff is indicative of the composition of the mineral, and there are minerals that are actually really common on Earth. And so the ones that we look at a lot are pyroxene and olivine. For Vesta, it's pyroxene, and so we can see the absorption features that tell us what kind of pyroxene, so like essentially how much iron is in that mineral structure that we see, and then we can do some really in-depth diagnostic studies of the various different meteorites and their comparisons to the various different members of Vesta and the Vesta family.
What type of asteroid? Like we talked a little bit with our previous guest Al about the different classifications of asteroid. Can you run us through them in your words? Because I'm gonna be honest with you, Al gave me like a whole bunch of different classification systems, and I don't know what he's talking about. And what is Vesta?
It's a V type for Vesta. Because
Is that just the first letter of the name?
It's
Is that
just
how you
that
type it?
important. It gets its own letter. Just
yeah. So the first several that we came up with, the way that we assign those letters are actually really self-explanatory. The S types, which are also very, very common, they're called S because they're silicate rich, which is that kind of mineral that we're looking at. And the C's are carbonaceous rich. They look like carbonaceous chondrites. So there we are.
I got a question for you. That's going to sound really dumb. This shows you the level of expertise I'm at. I keep hearing from geologists carbonaceous chondrite. What is that? Just dirt? What does that actually mean in like English terms?
In English terms, so that is amongst the most primitive, and I'm going to use big air quotes there, primitive of the meteorite types that we have. And so, if you think about this forming the solar system, you have all sorts of stuff, and you try to get that stuff to stick together, and eventually you make planets and you make all the other asteroids and things like that. A lot of stuff gets hot and it melts, and that takes you away from that primitive space. And so really the most primitive stuff in the solar system is going to be the comets. But when we're thinking about asteroids, we just kind of don't think about the comets. They're something else. And then everything else, kind of falls into this discussion. And so carbonaceous chondrites maybe got a little warm enough that maybe a little bit of liquid was moving through them so that you get what's called aqueous alteration. But it doesn't get hot enough to melt. And so that's the big thing that keeps the primitive types away from the things that look like Vesta, which melted and presumably has an iron core, and has all of these other kind of onion shell things all the way up to the crust.
So Vesta, you said is V type. What is V? Okay, obviously V type stands for Vesta is what I'm going to assume from this. No,
Yeah.
or does it stand for some mineral?
No, it stands for Vesta.
What does that mean? Is it just its own type? Like it's just a special asteroid?
Yeah, I mean there really aren't very many V types. There's the family that comes from Vesta, and there's a handful of others, but there really aren't very many, all things considered.
So
I
is
don't
it
even know what other things we would consider. So Vesta went molten at some point, is what I think I heard you say.
Yep.
How big? Like, what's the transition on like, oh, an asteroid beneath this size? No way is that ever going to have been molten, or we wouldn't expect it to. Versus like, okay, at this size, it's going to be big enough that it will be molten at some point in its past.
Right. I mean, I think some of that depends on exactly where you formed with respect to the sun, because there's some relationship between how far away you are from the sun and how quickly things start to collect together. And the thing that's driving a lot of this is both the accretionary heat for things hitting each other, but also you're collecting this radioactive element called aluminum-26. And so you need to collect enough aluminum-26 before there's no more and before the action essentially stops and moves on to a different phase. And so that's going to be what dictates your size. From where we can see now, we have a pretty good idea of what melted and what didn't based on the spectra. And so we know that there are a lot of objects that went through this process called differentiation. Once you melt, all the heavy stuff sinks to the center and the light stuff floats to the top. And we know that this happened a lot because we have a ton of different metal meteorites. And those came from somewhere. Those objects broke up and all the pieces flew out into space. Some of them came here. But right now, when we look back out, we don't see a ton of evidence of those kinds of objects still being out there, aside from some of the largest objects.
Help us like, obviously we care a lot about these special ones called metal asteroids, right? That's what
Right.
we're primarily going on. And I
The
believe
M types
the
for
M
metal.
types, right? That actually stands for Matt. But we will
It does
we'll talk
not.
about that every time.
I mean, if he
You
has his
worked
way,
with-
it will.
You worked with Lindy
Fair.
before this, right? On Psyche. Were you involved with the Psyche mission at all?
I went to some of the early workshops, and I didn't end up on the mission because I went in a different direction and got involved with Dart and everything. But when I was in graduate school, Lindy was one of the professors in the department, so I've known her for quite a while.
Awesome. Can you dive in a little bit with us and help us? Like, obviously, we have a whole bunch of metal meteorites here. How are metal asteroids formed? Where do they come from?
Well, metal asteroids come from when you take one of these objects that were differentiated, right? So you have the whole thing melted, the heavy stuff went to the inside, and then something happens to, in the technical term, catastrophically disrupt. So the whole thing was destroyed somehow. And you had to, break open all of the pieces and let that core out into many different pieces. And so one of the ideas behind Psyche is that, that is essentially just the core that was left behind, and all of the stuff that was on top has been dispersed and destroyed. And so there's a lot of big questions about what happened to all of the stuff that was on top of those metal asteroids or those metal meteorites that we have now, because we don't see those. They're not completely in our meteorite collection. So where did they go? I don't know.
What do you mean we don't see them in our meteorite collection?
It looks like everything that has a chemical composition that suggested it melted really looks like Vesta. And so unless we just are essentially over-interpreting it so that we think they all came from Vesta, but they didn't, then we can't account for them. And they're not still in the main belt as far as we could see either. So
What you just mentioned the main belt. What's the relationship between asteroids in near Earth asteroids and main belt asteroids? And like, do they have the same classification system? Like, how do we think about the connection between these two I'm going to use population loosely. I think that's correct, but correct me if I'm wrong.
Yeah, I mean, all of the near Earth asteroids are originally from the main belt. There's many different escape mechanisms from the asteroid belt into near Earth space. And once you get into near Earth space, you have a relatively short dynamical lifetime, tens of millions of years. And so you're either going to hit a planet, hit the sun, get tossed out, and that's it. And so that population is constantly being replenished from the main belt.
Got it. Okay. So we talked about.
Hold on, you're missing the question that I want to ask. Is like, cool, they all come from the main belt. Where does the main belt come from? Is it like, is this a planet that exploded? That's what I tell people when I don't actually.
I mean, like, that's an actual hard question. So the main belt is the planet that never was, right? Jupiter was too big. It just never really got going into a full-on planet. But there's a lot of debate about where the main belt came from. There's some large number of objects that clearly formed there, and there's a lot of objects that probably came from somewhere else and were placed in the main belt later. When, how, which ones, all of that. Some of that's still up for debate. And some of those objects then also find their way into near Earth space and end up being these weird different types that are maybe dying comets or something like that.
What do you think? Like, I get there's a whole bunch of debate. I want to hear the Cristina philosophy. Like, you just said that some of these metal asteroids are believed to be a planet that blew up at some point by the Death Star, right? And orbit. Like, do you think this is a planet that exploded? Is it a planet that didn't form? What's your thesis?
Well, I mean, in terms of the M types, I think that's definitely a planet that formed there, like a protoplanet, not Earth-sized planet, but something smaller, and that was then destroyed. Empire Strikes Back style, John Williams soundtrack, all that.
You heard it here first, folks.
Is
There
that
was a
actually
Death Star.
is that our first Death Star reference in 13
Yeah, and let's not
podcasts?
make any more. It's so overplayed. Like, let's just not go that route. After Disney
I'm-
bought it, like, that was a disaster. Can we just stop? Let's get back on track, chap. Stick to the script.
I am script. I like that you think that
There's
there's
a
a script that
script.
exists here.
Wait a minute. Why didn't I get a script?
Um, okay, so we've got all, do we have the exhaustive list as far as like listeners are concerned of types of asteroids, or are there more types of asteroids?
I mean, I think that you could do this any way you want. You could make more types of asteroids. And people are constantly making more types of asteroids. And they look at new wavelength regions and they're like, should we make more types of asteroids? And I think at some point it's not helpful. And so we mostly stick to the core groups, and there is
Yep.
a specific taxonomy that most people use that's from about 15 years ago. And we're trying to stick with that. And even then, if you go farther back in time to the older taxonomies, we're trying to keep the same letters because
Yep.
eventually it just becomes alphabet soup if you don't.
Okay,
So,
cool. Well, thank you for keeping it simple for us because it's definitely like I remember I was like really like keyed in on like cool, I know what an M type is, and then someone just casually threw out an X type, and I was like, hold on, what is that? And then that just like threw me off my game.
Do you
Okay.
mean by casually sometime the last podcast?
No, I was prepared for that one. It was prior to that when I was on a call with, I forget what telescope it was, and it just mentioned X type, and I literally just like did a timeout in the middle of the call and was like, you gotta break this down for me. Um, okay, so these are the types. You like spectral data. How do you get spectral data? And like how hard is it? How do you analyze it? Like walk us through like we're working with you, and I guess a little bit of framing for everybody listening. We're working with you to help us find M-type asteroids out there. How do you think about going about that job?
right. I mean, if you think about spectroscopy and collecting asteroids, we tend to use a variety of facilities. One of the things about looking at near Earth objects is that your telescope has to be really good at looking at near Earth objects. They move really fast against the background of the stars, and many telescopes are really well suited for tracking the movement of the stars. But once you add that extra motion in, they kind of just can't follow along as well. And so there's a handful of telescopes that do that very well. And the one that basically the entire community uses is the NASA Infrared Telescope Facility, or the IRTF. And so it has a really nice spectrograph on it. It's fairly simple from an engineering standpoint so that we don't lose a lot of light in the instrument itself. And people know how to use it really well. We've been using it for 20, 25 years.
Yeah.
And so we collect a lot of data from there. Essentially, what we do is we're sending light through a prism. The prism breaks it up like a rainbow, and then it spreads the light over, and we get an image that looks like a bright line that goes down the middle, or maybe a faint line, because many of them are actually really faint. So it's like a single line. And what we have to do is then extract that by understanding how the light is spread out to then convert that into the reflectance spectrum that is what we actually want to see.
Okay, IRTF. This is, and I'm sure you picked it because it was in Hawaii. Um,
If I got to go there, then yes.
you don't actually get to go there, so
I
you
haven't
are
been there
you?
in 20 years.
Wow. So do you get the free time? Like we just talked with this guy Al who runs LBTO or does something in LBTO, and he said there's three ways to do it. Do you get the director's discretionary time, or do you have to submit the proposals?
So I submit the proposals, and I ask for essentially one night every month, sometime around when we expect new objects to be discovered. So usually pretty close to new moon. And then I try to pick up essentially what is bright and what we're predicting is going to be interesting, which may or may not be the ones that people actually care about 6 months later.
Help me understand. So, you've kind of mentioned like we talked about the visual telescope. Obviously,
Mhm.
the angle matters. So if we look at a planet like Jupiter, we can get a whole bunch of different pixels of light.
Right.
I'm assuming there's the same philosophy with spectral sensors, but does it work the same? How do you think about it on asteroids?
Well, when you think about it with Jupiter, you can get a different spectrum of, say, the North Pole and the South Pole um, using all sorts of different telescopes, but you can't do that with basically all of the asteroids. They're all just point sources. And
And that's
so
just because they're too small.
they're too small, and the resolution of all of the instruments doesn't really work. There are a few cases with something like JWST where you can get, a few pixels across some of the largest ones, but that's about it. So
Did you get
unfortunately,
time on JWST?
I did. I
Does it have a
did.
spectral sensor on it?
Yeah, it has It has both. Well, I think it has three. I only really think about two of them as really applicable for asteroids. But we can look at the near infrared with an instrument called NIRSpec, and then there's a mid-infrared spectrograph that goes all the way out to about 26.5 microns. And so there's a whole extra set of features out there that we can use to study all sorts of stuff.
What does the infrared spectrum tell you?
Well, most of the things that people want to study using JWST is what's called the 3 micron region. And so you can't get that from the ground. You can get out to about 2.5 microns from the ground. But 3 microns is where water absorbs. And so since there's a lot of water between our telescopes and the asteroid in our atmosphere, which is mostly good for us, that turns out to be really detrimental to understanding hydration on other objects. And so that becomes a really big deal when you're thinking about the delivery of water from asteroids to Earth and how we actually, we're able to become a habitable world and all things like that. When it comes to the mysterious M types and the X types and all the things that are related, that is one of the indicators that we don't actually think it's metallic. And so that's one of the reasons people like to look at M types in the 3 micron region, because if it does have a large absorption that's indicative of water, that's probably not going to be something that we should assume is metallic.
So metal asteroids we don't expect to have, which I guess would make sense if we think they're this core of the planet that exploded that a whole bunch of people lived on. So they're just a solid piece of metal.
Yeah. There are some exceptions. If we go back to Vesta, we sent a spacecraft there. Dawn was there, and they found out that there was all sorts of carbonaceous conduit material on Vesta. So it actually had a small 3 micron feature that wasn't really what we expected when we were just thinking about it as an object. And so there's a possibility that some material has fallen down and is showing up in that region. But for the most part, if it has a 3 micron feature, we don't think it's metallic.
So what, like, as we think about trying to find M types, like what's the combination of data that you come back to us and say, hey, I am 100% confident that this is an M type and it's a small one, right? Because we care about Vesta. I looked it up, is 527 kilometers in diameter. Like that's not what we're going for. We're going for much smaller than that.
What is that in normal units?
300 and something miles, probably.
Okay.
You can fact check me on that, like 350, something like that.
I mean, everybody else operates in metric. I'm just
not us.
Not true.
What do you like? What is a? Oh, cool. I am 100% confident this is an M-type asteroid.
I mean, right now, as far as our current understanding goes, that could be as much as understanding how reflected it is to the radar, understanding how reflective it is to light, so the albedo, and understanding the spectrum. And so that's three different things that together should tell you if it's metallic, right? And so the spectrum, unfortunately, we've kind of alluded to this. The M types fit within the X class, and the X class can be all sorts of things. And so to understand whether or not it's actually M type, we usually use albedo. So there's this very specific albedo range that we ascribe to the M type. And then there's all sorts of other stuff that you can think about, like I said, with the 3 micron feature, or you could see if it's really reflective in radar. And so if you send out that radio signal and it is very, very shiny, then that's probably metallic. Essentially, the radar reflectivity is in a range that's essentially unique.
Yeah. And I'm one of the few people who's probably spent a decent amount of time playing around in the small bodies database from JPL. And it seems like there's a lot of, let's just say, conflict on how things are classified, or disagreement. Conflict seems a little too violent. Why is that?
I mean, I think that there's a handful of ways you can do it. And so, there's some older classifications that come when we were just using visible wavelengths, for example, and then we get newer data in near infrared wavelengths, which both covers a wider wavelength region, but also has better spectral features for many of the spectral types. So then you update it, and people hold on to the old classification and they say that it's from this other thing, and then they have the updated one, and maybe they're not the same. And sometimes that's really confusing. And then other times we have people who observe an object that someone else observed 5 years ago and it looks different. And so their classifications aren't the same. That mostly happens with things that don't have a lot of really distinct features. And so that's, the C types, they're pretty flat. Some of the X types don't have very many features. Maybe it has a little bit of a spectral slope to it. But if you're looking at Vesta, really big absorption features, those tend to get classified the same way every time. Not a lot of disagreement there.
Can you break down? So we talk a lot about how many different near Earth objects there are and asteroids, and then we sort of get into different classifications like, oh, there's this many, and there's this, like, we're only interested in M type, and of the M type, we're really only interested in this size and this size. Like, what are some of like the numbers and the breakdown?
Like, how many M types are there?
Yeah.
How many do you think? So there is a big study from the survey that I run. So I run this survey called MythNeos, the MIT Hawaii Near Earth Object Spectroscopic Survey. Kind of a lot.
That's an acronym of acronyms. I love it.
It really is. It's kind of a mess. There's also only one S, but there's two S. Anyway, it's fine. Anyway, so so they looked at the population, or we looked at the population, and thought about how to do something called debiasing, and that's essentially saying S types and V types are really, really bright. They're easy to find. Some of these other types are not as bright, so they're harder to find and harder to observe. How do you make the playing field a bit more even to understand exactly how many of each type of object there are? And so the S types, there's a ton of them. In near Earth space, there's like 66% are going to be S type. The M types, we're talking more like 3 to 5%.
And how many total asteroids do we think there are in near Earth space? I mean, I read a paper it's papers that predict up to 10 million. Where do you fall on this? Like, what does your crystal ball tell you?
Not sure. I mean, I think that it also depends on when you stop calling it an asteroid, right? At some point, it's just dust, right? And so where do you draw the line, and how do you draw that out? And so right now there's something like 38,000 known near Earth objects. I think that there's considerably more than that. I don't know that there's 10 million, but I think we're actually going to have a really good idea really soon. We have this big survey starting at the Rubin Observatory in Chile, hopefully later this year. And there's a lot of predictions about how many objects they're going to find that is based on how many objects you think there are. And so you can see how quickly they start to discover objects and start to match them to the different models. And so I'm really curious about that. That's been one of the big things that we've been looking forward to for quite a while.
Does that survey have an acronym that's a group of acronyms?
The survey itself is called LSST, which used to be the name of the telescope, but then they named the survey that, and so now it's the Legacy Survey of Space and Time. But it used to be the Large Synoptic Survey Telescope. We love acronyms.
Is the new telescope only three letters instead of four? Because that's the trend, right? Like, we've gone from 4-letter telescopes to 3.
To 3. Well, I mean, I think they're just calling it by the name for this one. This was just Rubin.
Wow.
Yeah.
All right. Matt loves acronyms.
Haven't we asked you about M types that we should be asking you?
I mean, that's a good question. Let's see. So I think one of the things that we haven't talked about when it comes to M types is that, we've sent spacecraft missions, we've sent them to S types, we've sent them to C types, we've done all these things. We haven't gone to an M type yet. We're on our way. We're on our way to Psyche. We haven't seen it. And so what does that mean? What is our effective ground truth? And then how do we put that back into our analysis methods? Because every time we go somewhere, we realize that at least one of our assumptions was completely wrong. And when we went to Bennu, we realized that we were measuring this property called thermal inertia, making predictions about what the particle size was going to be on the surface. That was not right. changed the
Christina,
entire way.
how did we
Yeah.
get Bennu so wrong? Like my understanding was that they did not, and I'm not a scientist, right? I'm not an asteroid physicist, so maybe this was just me reading hate pieces. But like my understanding is we thought it was solid and we got there and like, no, it actually had no, it was just this kind of pile of dust stuck together with static electricity. How did we screw it up so bad?
I mean, so we thought it was going to be really dusty because they knew that they wanted to take a sample. So that's one of the reasons that that all of it was designed to that spec, right? They wanted to go to an object that they thought was going to be dusty, and then they got there, and it kind of was, but it was more blocky, more boulders, more things like that. And I think that comes really, really low gravity physics comes into play there. If you have a really loosely consolidated boulder that's probably stuck together by something like static electricity, it's still a boulder, and you probably still can't take a sample from it because of the way that your spacecraft has to interact with the surface, but it might still have the properties from an outside observer of just dust. And so
Did you expect Dart was my understanding too was Dart went to, I forget the name of the two asteroids, but the one it hit was also just held together by it was very similar to Bennu. Did you
yeah,
guys make the correct prediction there, or was that off?
Didymos and Dimorphos. So Dimorphos was the satellite that we impacted. In some respects, because it was an experiment, the outcome would be different based on what we actually saw. I think we all thought it was going to be kind of this blocky rubble pile type object like we saw, but we were really excited when we saw it the first time, right? Right as the spacecraft was coming in for impact, because in that experiment, you wanted it to be blocky because you wanted that ejecta. That ejecta had extra momentum with it, which means that the orbital change was going to be larger. And so that was a big win for us. If it had been just a single rock, we still would have moved it, but it wouldn't have been by as much.
It was one of the coolest missions to watch, especially like when you saw the images coming through of it, as it gets closer and closer right before impact. I will say that I never thought NASA had really antiquated technology till I watched that live stream. That live stream like fits perfectly in the late 80s if you rewatch it, right? Like it's amazing. Amazing, amazing sets.
What was like your favorite mission to get data from and that you've worked on? Like what's awesome for you?
I mean, Dart was fantastic. It was a little bit more on, and I think that's probably not even the right to say. It was wildly more experimental than
Hmm.
basically all of the other missions. It was a different class of mission. There were different kinds of risks. There were things that were going up as technology demonstrations, but also, you know, we weren't sure how that change was going to happen, whether or not we were actually going to make a really large change to the orbit. And as a telescope observer, it was really exciting that the telescopes were a big part of the mission overall. And so there are a lot of pieces that really fit together. And then, if you take that off and you just put pure science hat on, we're going back with a European Space Agency mission called Hera to essentially assess the damage and figure out exactly how all of these pieces fit together from like a pure science perspective. What does the spectral distribution of the surface look like? What does the crater look like? Is it a crater? There's a lot of predictions that say that we actually reshaped the entire object because of the weird low gravity physics.
Oh,
Um,
that sounds like so cool.
so I'm still super pumped about Didymos Dimorphos.
If we made you CEO for a day and we just kicked Matt out of the building for the day, what would you have us
Wait,
do for an
whoa,
experiment?
why limit to a day? Oh,
Sorry, we'll give you a longer period of time. You discover you dictate the time. What would you want us to do?
I mean, for a lot of things, including, finding the M types, I think one of the big pieces that's missing is that there's a lot of types that we haven't studied. We've gone to S types and C types, like I said, and the B types, which is where Bennu comes in, which is part of the C group. But there's a lot of objects that we don't have a really fundamental understanding of, and so one of the proposals that I was on a while back to NASA was to take an asteroid tour. and to just, fly by a ton of objects so that you can understand exactly what's happening on a whole bunch of different objects, a whole bunch of different sizes, different physical properties, all of this stuff to just really start to understand what the space is. Because there's still some really fundamental gaps out there.
If one of our 45 listeners is from NASA, we actually did some trajectories on this, Christina, and we're able to see with the next upcoming mission, we can do a flyby of about 13 different bodies pretty easily. There's some ways to get more, there's some ways to get less, right? But this is not a hard thing to do, and I wish NASA does do kind of a grand tour part two, but instead of the planets, we go to a whole bunch of asteroids.
No, it'd be great.
Okay, well let's make sure NASA puts us into the budget, even though it got cut in half. I think this is a great mission to spend it on.
I like that you're going to use the podcast to do that. That's definitely our most effective way to get into NASA's budget right now.
100%, 100%.
Awesome. Should we do final round questions? I feel like this is a good mechanic. We should just keep going with it. Robin, I'm put you on the spot.
Oh, nice. Yeah. Final round of questions. Never chat first. That's fine. I got you. I guess I'm thinking about like all the different types of asteroids that you've talked about and how we know some information about a lot of them, right? And I'm like in my mind, I'm imagining this infographic.
Can you just ask the question?
Damn. I'm trying to figure out how much we actually know about the different asteroids that are out there, right? Like, because you said they're all like smaller than a pixel, right? From what we can observe. Cool. So we know a little bit about a lot, but we don't really know that much about most. So what, like,
Still waiting for your question.
I'm trying to figure out what the scale is. Like, what's the scale of knowledge on asteroids?
I mean, I think you're absolutely right. Like, there's a lot of objects that we have very little idea of what's going on with them. We have a sense of maybe how big they are, from how much light we get, but that's about it. And so the question is, how do we improve that? And so we have a lot of really big scale surveys. So like I said, the Rubin Observatory is supposed to start their survey. And one of the things that they're going to do along the way is to take what I think of as spectral photometry. And so we're taking different filters of light and using that as a really rough spectrum. And so ideally, we can have catalogs of tens of thousands of asteroids in a decade that have just wandered through the Rubin Observatory's survey. And then we can use that to maybe not have super refined understanding of objects, but to have this really base level understanding of a lot of objects. And so I'm hoping that will really help us. There have been surveys similar to that in the past, but on smaller scales. And so I think that by having more objects and having a much larger telescope than many of these past surveys so that we can go fainter will also just help our knowledge base of what the overall population looks like. Not just the NEO population, but the main belt population too.
All right, I got a way
Matt, what
better
do you got?
question than that. Christina, this is a very serious question.
All right.
And I'd like to know your educated approach to it. Do aliens exist?
Oh, let's see. Do you count like bacteria?
Yes. I want to know, like, what's your
Sure,
thoughts? Like, does life exist in the universe? Obviously, I think it's
What's
almost
the question, Matt?
conclusion. I'm asking it a lot better than you did, Robin. I guess I'll ask it differently. Does intelligent life exist in the universe?
I don't know. I mean, it's possible. I certainly don't think that we've been visited. I don't think we, have some secret Roswell base, but well, it's possible it's a really big universe. But
Where do you think we'll first find bacterial life, like or little microbes, right? As we look out into the cosmos, where do you think we're going to find that?
I mean, it's entirely possible we find that on, Europa or something, right?
Would Europa Clipper, does that mission actually have the capability to detect life if it's there?
Not entirely. I think it can detect things that are indicative of life, which is different.
Okay.
Yeah.
Okay. Chap,
We
you're
should
up.
totally fly a mission to contaminate Europa.
That seems real in scope. I'm sure investors are going to love that. Can't wait to make that pitch slide. All right. I'm going to fast forward into the future. We're like, call it 18 to 24 months from now. We're celebrating because Vestry is actually rendezvoused with an asteroid that you will help us find. What are you most excited slash surprised to discover that we found on that M-type asteroid?
Ooh, I mean, I'm really excited to see what M-type asteroid means. Does it mean, is it completely metal? Does it mean it's mostly metal? Are there rocks on it? What kind? We have
Yeah.
these really crazy artist renditions of Psyche with these giant metal spires, and I really don't think that's quite what we're looking at. But what does an M-type asteroid actually mean? I have no real physical intuition for that, and I'm really, really pumped to see what that actually means.
Okay. Um, Second part of that question, because this got the mic and I can do it. We bring you back a piece of metal. What's the first thing you make out of that metal?
Since when does the last question you get two? What I mean,
We just started doing last question like 2 hours ago, so
Yeah,
give
but
me
it's
a
the
little
last
leeway
question,
here.
not last two questions.
Once again, question stands. You get a chunk of metal that came from an asteroid. What are you making?
What am I like? Do I know how to make things out of metal in
Sure.
this world?
Yeah. Yeah.
wow. That's what you
Um,
get for asking two questions, chap.
is this like a King Tut style dagger? Is that good?
Yeah, that's a perfect one to end
Okay.
on. Awesome. Dr. Cristina Thomas, thank you for putting up with us. We really appreciate you teaching us all about M-type asteroids. All listeners, thank you for listening, and please subscribe and leave us some reviews.
There
That's
is
all
no
for
way
Roid
my
Don't
Rage.
say
passion
that
for
at the end.
best.
Don't do that. If you like it, you'll know how to subscribe. I don't want to advertise
Just,
that.
just
So
We
so
gotta do it.
bad.
We
Like,
gotta
no,
do
you
it.
don't. No, you don't.
We
Nobody's.
do.
I've never heard subscribe and view in a podcast. I'm like, oh, let me go subscribe. I'm like, I actually hate these people.
Well, I mean, thank you for telling me how you feel.
I'm leaving.
All right.
therapy.